You don't have to. All right, ladies and gentlemen, today's class recording has begun. So, yesterday, I change it up a little bit, I don't want to get too stale. So. All right, yesterday, we used Newton's second law to examine the acceleration of a skydiver at different points of his fall. And so we talked about at the very, very beginning of this skydiver's flight, his velocity is 0, but he has a very large acceleration, so he picks up speed quickly. A result of picking up speed quickly is that he now encounters air resistance, right? He's running into those particles that make up the atmosphere, and they exert a force on him, but in the other direction. And so now he encounters an air resistance force. That makes his net force decrease, and that makes his acceleration decrease. However, we had this discussion. Just because his acceleration is smaller doesn't necessarily mean he's slowing down, right? He doesn't start slowing down until what happens to his acceleration? It becomes negative. Here, it's still a positive acceleration. He's still speeding up. He's just not speeding up as much. Does that make sense? Right? His velocity isn't increasing as much. And that will continue, and as he continues to go faster and faster and faster, he will encounter more and more air resistance. And there comes a point when the amount of air resistance he feels is exactly the same as the gravity that's acting on it. And so, net force is 0, and acceleration is 0. And Shane, we refer to this as terminal velocity, and we'll explain this a little bit more as we go along here, okay? Unless a different force acts on him or his speed changes, this is not going to change, right? Constant velocity will continue. So the opening of the parachute increases the resistance force, not because he goes faster, but because there's more area that he's running into things. Now, the net force is negative. There's more upward force than downward force. And remember, we talked about downward being positive and upward being negative, right? So there's more up than down. That means the net force is negative. That means the acceleration is negative. Has he turned around here? No. He's doing what? He's slowing down, right? Still moving in the downward direction, but negative acceleration means he's slowing down while moving in the negative acceleration. As the parachute gets bigger, this resistance force gets bigger and causes him to slow down more. But slowing down more actually results in less air resistance. Does that make sense? You're moving not as fast. Are you running into as many air particles anymore? Nope. And so eventually, this happens again. All right? What's the net force in this picture? 0. What's the acceleration in this picture? 0. Shane, what do we call this?
Terminal velocity.
Terminal velocity. Is it the same terminal velocity as before? No, because Bronco falling through the air without his parachute is different than Bronco falling through the air with his parachute. Different terminal velocities, but still acceleration, come on, pen, still acceleration equal to 0. Okay? Good there? Okay with that? All right. What's the one thing that never changed in all of our pictures? His weight, right? His mass too, right? But his weight force, this force of gravity pulling down on him, remained the same the entire time. So let's talk about why that is. All right. So today, we're going to talk a little bit about gravity and how gravity does the thing that it does to these objects. We've discussed gravity before. What have we talked about in terms of gravity previously? It causes a what? What kind of acceleration? A constant acceleration. Knowing what we know now, if gravity is causing a constant acceleration, what does that mean gravity is? A force, because force causes acceleration, right? So, that being said, right, gravity. Gravity is an attractive force that exists between any two objects. Or if you want to be a little bit more specific, any two objects with mass. But you can't be an object if you don't have mass, so it's kind of redundant, but whatever. Okay? The fact that it's an attractive force means it does what? Pulls things together, right? Now, we talked about this a little, I think, on the first day of this unit, but it's an important concept when we're talking about gravity. Okay? Gravity is not something that one object does to another object. Right? Gravity exists between two things. You can't have an object that has gravity if there's not another object for it to interact with. Okay? We think about gravity a lot of times as something that the Earth does to other objects. But really, gravity exists between the Earth and that object. Or that object and some other object. Or the Earth and the sun. You have to have two things in order for gravity to work. Right? A lot of times we think about gravity, like I said, as something that Earth does to things because we toss this ball, it slows down, it changes directions, it speeds back up, and the Earth doesn't do anything, right? But really there has to be two objects to make it work. Okay? Good there? All right. There's a couple factors that affect the amount of gravity. First, it depends on the mass of the two objects. And there is a direct relationship there. The more mass two objects have, or one object has for that sake, right, the more gravity exists between those objects, right? Gravity exists between the Earth and this ball. If I took this baseball to the moon, how much gravity would it be acting on it? Well, compared to the gravity that it experiences here on Earth. Less, right? Because the moon has less mass than the Earth, and mass is directly related to the amount of gravity, right? Mass goes down, the amount of gravity goes down. Okay? Good there? The second thing it depends on, and I don't know why this came up this way, but it did, right? That's just, this second line is just explaining direct relationships, right? Which I think we have that down now. Good. The next one, it depends on distance, and distance has an inverse relationship. Technically, it's an inverse square relationship, but I won't hold you responsible for that right now because it gets a little bit confusing. Okay? So, if distance and gravity have an inverse relationship, what does that mean? Go good. If distance increases, the gravity decreases, right? So technically, as I take this baseball and I go from here to here, what happened to the amount of gravity that's acting on it? Technically, it decreased, okay? But when we talk about distances, we have to talk about distances from the middle of the object, all right? So, right? That was pretty good. Yeah. Wait till you check this out. I mean, this is going to be heavy.
Wait, is the blue supposed to be the water?
Well, yeah, like North America and South America are connected.
And Hawaii. Thank you.
Hawaii really is like it's Hawaii is like really far away from.
What about the Dominican Republic Islands?
There's Cuba, you know. So this is not to make light of the situation, but like Puerto Rico is not green anymore, it's brown because all the leaves. It's like if you look at satellite pictures, no, it's true. Like if you look at satellite pictures of Puerto Rico before the hurricane and after the hurricane came by, like all the green is just gone. Just like, maybe if we get at the end of this, yeah, all right, so anyway. All right, so if we talk about not to scale, okay, if we talk, we have to go over here. I know you can't, here, we'll go here, and whatever, okay. So, right? Yeah, so this is completely false. Yes, absolutely. Kyrie said so it must be true, right? All right.
There's no pictures of her.
There are tons of pictures of her.
He said there's not.
Yes, but there really are. So, yeah.
The internet doesn't lie.
What?
The internet does not lie.
No, you can't put anything on the internet that's not true. Like, all right, so when we talk about distance, we have to talk about the distance to the center of the object. So this baseball might be 2 meters off the surface of the earth. But it's 16. This many meters to the center of the earth. Yeah, it's pretty close, like 6 million meters. It's like 6,300 kilometers. So, right? So if I take this baseball and I move it from here to here, technically am I moving it farther away from the center of the earth? Technically. But compared to this value, is it really that much farther away from the earth? Not really. Okay? Also, when we send spaceships up into orbit, right? We'll put like a little satellite dish on this thing too. Okay, you know, okay, that's a pretty big. So, yeah, it's a pretty big satellite, right? Satellites are about 200 miles off the surface, which seems like a lot, but this is about 3,500 miles to the center. So even meters, miles. So yeah, just different because I can't remember how many meters like it is off the surface of the earth, but it's anyway. So yeah, I know those numbers in miles a little bit more. Okay. So even though we send something pretty far off the surface of the earth, when we send something into space, does it feel no gravity? No. It still feels a lot of gravity. And almost, it's not very much different than the gravity we feel on Earth. That's not why things behave like they do in space. That's something different, okay? But gravity exists between two objects. As we get farther away, it decreases, but when we talk about things close to Earth, we are always really close to Earth, most cases.
It's 3,950 miles.
Is that good?
Yeah.
Is there anything else you want to correct me on? Stuff runs back into the earth though. So, multiply that by 5,280.
Okay.
So, did you give me this meters number yet, or what?
Wait, you said multiply by what?
Oh no, that's something different. So, that would be how many feet?
637 kilometers, so like that's
Yeah, that's what I said.
All right. Good. What? Oh, it's just a sloppy M. See this right here? There's a little. Okay. All right. We will not use this picture ever again for the entire class. So I'm glad we got this much detail on it. So.
Wait, you forgot to do like the 3D. So like.
Okay. The one gravity that we obviously deal with most often is the gravity here on Earth. But like we discussed, Gravity isn't something that the Earth does to other things. It exists between things, right? Gravity here exerts a force on all of our objects. If gravity exerts a force on objects, it can do one of three things to them. What can it do?
Speed up, slow down,
Make it
or
speed
change
up,
direction.
or slow down,
Or change direction.
or change directions, right? That's what force does. Force causes acceleration. It can cause it to slow down, change directions, speed back up. Gravity does that just the same way any other force does. Okay? It's a force, it causes acceleration. It can cause things to speed up, or slow down, or change directions. Okay? The reason why we sometimes think of Earth's gravity as different than other kinds of gravities is that Earth's mass is so big, at least compared to us. Right? In the grand scheme of the universe, Earth's mass is not very big. But compared to us, Earth has a huge, huge, huge mass, and we are really, really close to it. So, big mass directly increases the gravity. Being close to it increases the gravity. So we feel Earth's gravity very, very strongly. But it's not any different than other gravities that exist out there in the universe. Okay? Good? Glad you're spending so much time on this drawing here. So,
It's that coloring.
I know. I see. Okay. So, we obviously can't get rid of Earth's gravity, right? We just talked about the idea that when we send things into space, they don't feel no gravity. They feel less gravity, but not a whole lot. And even as we go farther and farther and farther and farther and farther away, technically there's still some gravity between the Earth and us, right? The Voyager spacecraft that left the solar system, whatever, 10 years ago, or whatever it is, there's still some gravity that exists between Earth and that Voyager spacecraft, right? It's real small because the distance is very, very large, but there's still some gravity there, okay? All right, mass and weight. We talked about mass. Jason, go ahead.
You know the gravity on Earth and the gravity of the sun is basically holding us not in place, but in that circle.
Yes, yeah, yeah. Yeah.
Why not use that Voyager level off the sun?
Say again?
Like, okay, you know how you said Voyager feels whatever the thing that our solar system? Like,
Yeah.
it feels our gravity, right?
Yep.
Since the sun is so much bigger than ours, like, it feels the sun gravity more than ours.
Yes, it does.
But then, like, it just.
I know, it's kind of confusing, isn't it? Right?
But shouldn't it just, like, attract the sun stuff?
Yeah.
Say again?
Shouldn't it just attract the sun? Like, the gravity of the sun is so much larger, so it just goes straight to the sun.
True. But, so, if we compare gravity just in terms of mass, yes, the sun's gravity is bigger than all the other gravities in the solar system. But it also depends on distance too, right? So when I let this ball go, yes, it is attracted to the sun, but it's attracted to the Earth more. Not, the sun is bigger, but we're closer to the Earth, so that like overtakes the mass factor. Does that make sense?
But it's so away from Earth.
Right.
So wouldn't that just make sense?
What?
Since the sun is
So what we've actually done with it, all right, is, so this ball, right, if I throw it up, eventually it will slow down, stop, and come back down, right? I could prevent it from coming back down if I applied another force to it. Does that make sense? Like, it'll go so high when I throw it, but if halfway up somebody hit it, it would go higher, right? What we did with Voyager is, as it approached some other planets, yep, we used, so it ends up going faster, and while technically according to the math, there is still some gravitational attraction there, it's so, so, so small that effectively it doesn't really do anything. Is that okay, or is that not okay? As we get bigger and bigger and bigger, right? So,
It's okay. We should probably finish this lesson.
okay, that's fine. So, okay. As we get farther, there's less and less and less gravity, and we get to the point where effectively it's just not there anymore because it's so small, right? All right, mass. We talked about mass earlier in this unit. What does mass tell us about? How much stuff is there? How much matter is in it? But that also then affects what? The inertia that it has, right? So yes, mass is a matter of how much stuff, but the more stuff there is, the more inertia something has. The harder it is to get it to change what it's doing. Mass does not change regardless of where we are. This baseball has exactly the same mass here as if we took it to the moon. Okay? I mean, the baseball still has the same mass. No. Well, let's not go there. So, we're still learning the basic laws of the universe. Black holes sort of change the rules, and we're not ready. We're not quite ready for that just yet. So, okay. All right. So, the mass of this baseball doesn't change regardless of where we go. Meaning, if I take this baseball and I throw it here on Earth, right? Okay? If we went to the moon, you would have to throw it just as hard to get it to move just as fast. Okay? My force affecting the mass of this baseball doesn't change whether we are on the moon or on the Earth or on Mars or wherever.
Wouldn't it go not as far?
Okay. Where would it go not as far, Edie? No, on the moon it actually goes farther.
But not as fast.
Okay? So, Edie, right? If I take this baseball and I throw it upward, let's say I give it,
velocity is less.
say, no, what's less on the moon?
Gravity.
The acceleration is less. So if I throw this ball, let's say with a speed of 10 meters per second, okay? Do we remember from the last unit how long it would take to get to the top? It would take 1 second because gravity changes the velocity by how much here on Earth? About 10 for every second, okay? On the moon, gravity only changes the velocity of the ball. The acceleration is only about 2 meters per second. So if I took the same ball and threw it with the same speed, how long would it take to get to the top? 5 seconds, right? 10 to 8, 8 to 6, 6 to 4, 4 to 2, 2 to 0, right? So Edie, that's not any different in how I would throw it, okay? But what's different is what happens to it after it leaves my hand. It keeps going, or it changes less, so it goes farther, right? Because, right? The weight of an object does change because the weight is the force of gravity acting on an object. When you stand on the scale and it measures your weight, it's measuring not your inertia, but how hard is Earth's gravity pulling down on you. Technically, if you take your bathroom scale from the downstairs bathroom to the upstairs bathroom, what should happen to the reading? It should go down. Because why? Less gravity. Is it enough for you to notice? No. Okay. If you took that same bathroom scale and took it to the moon, what would happen to the reading? Be a lot less, right? Because there's way less gravity on the moon than there is here on the Earth.
No, that's what I meant to say.
What? Okay. Weight depends on the amount of gravity acting on the object, and it depends on the mass of the object. and the acceleration caused by gravity there. Okay? That's a lot of stuff. But when we calculate the weight of something, we multiply that object's mass by g. We said little g represents what? The what of gravity? The acceleration of gravity. So if we want to calculate the weight of something here on Earth, we take the mass of that object and multiply it by what? What number? 10 or 9.8. Right? Because that is the acceleration caused by gravity here on Earth. Okay? So, the weight of an object depends on the mass of that object and how strongly does gravity affect it at that location. Right? If we go to the moon and calculate the weight of an object on the moon, m doesn't change, but g would. Right? I just told you what's g on the moon. About 2, right? So things on the moon weigh about 1/5 of what they do here on Earth. Right? Not because this changes, but because the gravity changes. Okay? Good there. Okay? Which one weighs more? So, which one weighs more? The baseball, right? Your right, my left. Okay, I'm getting confused right there. Because what's true about the acceleration of gravity for both of these objects? It's the same, but this one has more mass, right? If this one weighs more, what does that mean? Does it? Doesn't.
Well, it's the same because gravity's the same.
But
No,
We
it
did
has more
this.
math.
right, we did do this. But if you think about it, right, now knowing what you know, it might not make as much sense as it did before. Because what is weight? It's a force, right? Which one's feeling more force? The baseball. It's all right. You can just call it the baseball and the ping pong ball. This one feels more force. But at the end of the day, Edie, what's true about the acceleration? The accelerations are the same. So that might contradict a little bit, right? But let's talk about why it actually happens. Okay? Okay? So, first, do objects weigh more on the moon or on the Earth? Do they weigh more? They weigh more on the Earth because more gravity. Do the objects have more mass on the moon or on the Earth? Neither. Right? The mass is exactly the same. Okay? All right, so let's talk about this. Okay? All right? It's pretty sweet outfit that she's got on right here. So. We discussed that girls can be astronauts. No girls ever went to the moon, but you know.
Okay, thanks for pointing that out.
I'm just saying. Maybe I was pointing out the inequity in NASA's selection system.
Yeah, God.
There were no female astronauts at that time. So, you know, first female astronaut was I think 1984. When did we go to the moon?
69.
1969. Well done.
Have you ever watched Men in Black?
Wow.
I actually have, but
Actually, no.
All right. So, getting back to this, right? We know that if we can isolate gravity and gravity only, what's true about the acceleration of this feather and this rock? They're exactly the same.
It was actually in 1983. Her name was Sally.
Sorry, Sally Ride. I apologize.
Sally.
Sally Ride was riding on a spaceship.
Wow. He just came up with that all on his own. All right, so we know we've seen video, which, to the best of my knowledge, is authentic. You know,
No.
Kyrie might disagree, but whatever. All right, so
I love Kyrie.
that if we can isolate just gravity, the acceleration of these objects is exactly the same. We learned earlier in this unit that acceleration depends on two things. What are the two things that acceleration depends on? Net force and mass. Okay? So, if there's no air resistance, which one would experience the greater net force? The baseball, right? It's got more gravity acting on it. And if there's no air resistance, gravity's the only force. So the bigger net force should make the baseball go faster, right? Direct relationship. More force, more acceleration. But which one has the greater mass? The baseball. What does mass do to the acceleration? If mass increases, acceleration decreases. So the greater force should make the baseball go faster. But the greater mass should make the baseball go slower. So what ends up happening? They basically cancel each other out and everybody goes the same acceleration. If we're talking about gravity and gravity only. Okay? So, let's talk about the last part of your outline, right? The acceleration of the objects depends on two things. Hassan, what are the two things that acceleration depends on? Net force and mass, right? So Roman numeral number 4, right? Number 1 is net force, number 2 is mass. Okay? So we just talked about, right, when these two objects are dropped. Which one feels more net force? Baseball, or the one with more mass. So that should make the acceleration go up. But because it has more mass, what does that do to the acceleration? Makes it go down. So the increase in force is balanced out by the increase in mass, and everybody experiences the same acceleration. Right? Is that good? Put it into words somehow at the bottom of that page. Okay? Well, I just did, right? Okay, so heavier objects experience what? Greater what? Net force. Okay? Heavier objects experience greater net force. But heavier objects also have more mass. Okay? More net force should do what to the acceleration? Increase it. But more mass does what to the acceleration? Decreases it. More force trying to increase the acceleration, more mass slowing down the acceleration means what ends up happening with the acceleration. They're all the same. Okay? Is that good? All right. So the back of the page talks about terminal velocity, but I think our discussion yesterday of Bronco and going through the air pretty much covers it. So tomorrow, for the first half of class, we'll go over some of the practice problems in the packet, and then you'll take the quiz the second half of the class. Okay? There is some homework stuff on the calendar if you want to check out some of those things. You can check it out there. A couple of practice problems dealing with mass and gravity.
Plus, it's